Assalamu alaikum wa rahmatullahi wa barakatuhu. Rabbi shrah li sadri wa yassir li amri wahlul 'uqdatam min lisani yafqahu qawli. Rabbi yassir wa la tu'assir wa tammim bil khair. So in this video we will continue our topic of DC machinery fundamentals. So in today's video we will see that how the voltage and the rotor windings of real DC machines be determined. So the voltage out of the armature of real DC machine is equal to the number of conductors per current path times the voltage on each conductor. So the voltage in any single conductor under pole faces was previously shown to be induced is equal to VBL. Now the voltage out of the armature of a real machine is thus then EA is equal to ZVBL over A. Now what are these constants? So where Z is the total number of conductors and A is the number of current paths, the velocity of each conductor in the rotor is V R omega. So E is equal to Z R omega BL over A. And we know that the phi is equal to B AP and A is the 2 pi RL. If there are P poles in the machine, then the total area A is AP is equal to A over P. So that will be 2 pi RL over P. If we just insert this here, so phi is equal to B AP, which is equal to B times 2 pi RL over P. So that will be here. Now, so the internally generated voltage in the machine can be expressed as this E is equal to ZR omega BL over A, and that can be written as ZP over 2 pi A and 2 pi RL P over P omega. Now here we can see that this ZP over 2 pi 2 phi A will be here same, and this is phi that we have calculated now, and now this is omega. So we'll put all these machine constants Z P over 2 pi A as K. So the internally generated voltage in the DC machine is equal to K phi omega. Similarly, we can have the torque induced in the armature of a real DC machines. As we know that the torque induced torque in a single conductor under pole faces is R times I conductor LB. If there are current paths in the machine, then the total armature current IA is split among the A current paths. So the current in a single conductor will be then IA over A. So and the torque in a single conductor on the rotor is then RIA-LB over A. So since there are Z conductors, so we can multiply it with Z. So the total induced torque in the DC machine will be ZRLBIA over A. So the flux per pole in these machines will be phi is equal to BAP, which is equal to B2 pi RL over P. And then if we just rearrange this equation, so this will be again 2 pi RL. If we just insert these sum of the values here by multiplying and dividing in this equation, in this equation, and similarly that we have done for the internally generated voltage EA. So we can find out that it will be ZP over 2 pi A phi IA, and phi is this actually 2 pi RLB over P, and then it will be written as K phi IA. Now K is again this machine constant, and we have seen that this is the same ZP over 2 pi A, ZP over 2 pi A, that is also produced, it was visible in this internally generated voltage. So here we can have the torque induced K phi IA. Now the most important thing to analyze these two equations actually, which are very important and which we will be using more frequently in our next chapter. So these are these EA, which is equal to K phi omega, and K phi IA. Now actually what actually happens that we can see that the speed is directly proportional to the internally generated voltage. Here we can see that EA is equal to omega. If we have somehow flux is constant, if we make this flux somehow constant, then we can easily say that EA is proportional to omega. Similarly, or EA is proportional to the speed. Similarly, if we can see this figure, if we have again assumed that we have made by somehow this flux constant, so K is already constant, so we can see that the induced torque is proportional to IA. So literally it means that if we want to increase the internally generated voltage, we can increase the speed, or if we can increase the internally generated voltage, we can have the infinite speed. But obviously machine constants are there, machine saturation is there, so we cannot have this situation. So it means that EA will be some finite value and speed will be again some finite value. Otherwise, mathematically we can see that EA is proportional to omega. If we increase EA, omega, the speed of the rotor will be increased, or if we increase the E omega, the internally generated voltage will be increased. Means in both ways, if we are using it as a motor, we will increase EA and we can have the means as much speed as we want. And if we have using a generator, so we can use the prime mover, and we can rotate it at any speed to get any voltage in this motor. But obviously there are machine constants and there are saturations. We know that from our previous knowledge that that would not be possible, so obviously there will be certain limitations. And similarly here, if we increase the IA, so we can visualize this mathematically that torque induced is proportional to IA. But torque induced will obviously, if it is a motor, then we are supplying this IA. So that will not be it's impossible that we can increase the IA to infinite and get the infinite torque out of a machine. So obviously again we have those certain limitations of the saturation and all those things, so we cannot have the infinite torque that can be produced in the machines. So obviously these two equations will give us a very good insight of the machine, that how we can have these two parameters that can be used separately to control obviously the speed and the torque of the motor. And IA obviously can be controlled by different methodologies to get the variable IA. So let's look at these power flow and losses in these DC machines. So obviously these are the basic relationships, and we have the efficiency, which is equal to output power minus losses over input times the 100%. So the losses in DC machines are mostly electrical or copper losses, which are known as the I square R losses. So one of them is the armature loss, IA square RA, and the other one is the field loss, which is IF square RA. Similarly, we have the brushes here, and there will be some drop on the voltage drop on the brushes. So we call it as the brushes power brushes drop, which will be VBD square IA. Similarly, these are the core losses, which cannot be removed from the motor, which are known as the hysteresis and eddy current losses. Then we have the mechanical losses, which can include friction and windage loss. There are some certain other losses which normally we cannot calculate directly, so we just put them in the stray loss. So this is our the power flow diagram for the generator, and this is the power flow diagram for the motor. So here for the generator we have the torque applied omega m, which is from the prime mover. We have some stray losses, then mechanical losses, then we have the core losses, and then power is converted here, and then we have the I square R losses, and then we have this output power, which is VT-IN. Similarly, if we have this input power, which is the terminal voltage time line currents, so we have some I square R losses, then there will be a power conversion, and we have the core losses, then we have the mechanical losses, we have the stray losses, and then we can have the mechanical output of the motor. So I hope you have understood these basics of the DC machinery fundamentals. So we will look in the depth of a little bit depth of these DC machines and generators in our next series of the videos. So still, if you have any questions in these topics, so you are welcome. You can ask any question anytime. Stay blessed. Assalamu alaikum wa rahmatullahi wa barakatuh.